So now what we're going to do is give some examples of techniques for ensuring safe publication in Java. So here are some things that need to take place in order for an object to be safely constructed and published. The reference to the object and the object's state must be made visible to other threads at the same time. This is a really, really subtle and bizarre thing. So there's a couple different ways to publish objects safely. Storing a reference to an object into a field protected by a lock. That's a real easy no-brainer. So here's an example where we have a singleton class, and as you can see in the instance method of singleton, which hopefully you recognize from the 251 class, it's going to synchronize on the class object, which every class has a class object. And by doing synchronized, that trivially makes sure that everything will be pushed out to other threads when the curly braces hit logically here when this critical section of code is done. So the lock ensures that both the reference, sinst, and the contents of what the reference references, namely the singleton object, will be pushed out or published to other threads when they get their shot at checking to see if inst is null. So that's one trivial way of doing things. The drawback with this approach is that every call to instance is synchronized. So it's going to be more synchronization than we really need, because we really only need to synchronize the first time in. Another way to ensure that an object is properly synchronized is storing a reference to it in a volatile. And you have to do this in a very careful way. If you make this static volatile, then this will ensure that the singleton instance is correctly synchronized. And this approach is an optimization of what we saw before. The first time in, we set sinst, which is this volatile field, to this result object. We check to see if result is null. If it is null, that's the first time in, then we have to acquire the lock. Otherwise, we skip over and just return the result. And this was a technique that was added to later versions of Java to support the double-checked locking optimization pattern. And the use of volatile will avoid the problems with partially constructed objects. This is especially built into the Java virtual machine to know how to propagate both the reference and the value of the object's values through the cache hierarchy. The drawback is that this particular approach only works with Java 5 and above. So that was added later, and you can read about that if you take a look at the double-check locking optimization Wikipedia page. It talks all about the history of this. Yet another thing you can do to make sure that both the reference and the object state are published is to store a reference to an object in a variable, in a volatile, or an atomic reference. So here's an interesting example that illustrates this. And this is somewhat like the grad student version of these spin lock, reentrant spin lock that we had for assignment 1B. So here we have atomic reference, which is static. We make an instance of it starting out with null. Then down here, we come along, and in the instance method for the singleton, we go ahead and check. We get whatever this is. The first time in, of course, it'll be null. In which case we go ahead and we make a new singleton object, and then we do a compare and set. And this compare and set will only be set the first time in. And remember, compare and set has the side effect of establishing a happens before relationship, which will ensure that the value of the singleton is pushed out to the other threads. Then we go ahead and update this value, depending on what we've already got, and return the value. So this approach works also and publishes the objects correctly. The downside is that it might turn out that multiple threads would come here at the same time, all find sing null, and all call singleton's constructor multiple times, one for every thread that happened to find sing null. Now, only one object will actually end up inside the atomic reference field, but the constructor could be called multiple times. Probably not a big deal for this example, but it could be a bigger deal if your constructors have some kind of side effect. Yet another thing you can do is use something that's called the the on-demand holder idiom, which you can read about here. And this is a clever approach for singletons, at least, that relies on the fact that the lazy holder class has to be initialized atomically by the Java execution environment, for example, the virtual machine. So this thing will get called once and only one time, and it'll be done atomically. And then this simply returns that inst. And so lazy holder will be initialized when the static method instance is invoked, which will trigger the virtual machine to load and initialize the lazy holder class. And that's also done atomically. That nice thing about that is it'll work in any version of Java. Then you can also store a reference to an object into a final field. This is another interesting thing to be aware of. So down here we have a non-final field and we have a final field. So non-final, m-non-final, and m-final. And here we go ahead and initialize a new object A, and it's guaranteed that this final field will be initialized properly by the time thread 2 gets to run, because it's final, but it's not guaranteed that this field will be initialized by the thread 2 runs, because it's not final. So final is yet another way to ensure this. And basically what do final fields do? Final fields are immutable, and they can always be used safely without any other form of synchronization, because once they're constructed, they always have the same value henceforth and for always. So a good example of an immutable object in Java is the string class, which doesn't allow the values to be changed after it's initialized. Now, this is also important. If a final field refers to a mutable object, synchronization is still needed to access the state of the referenced object. So in the case of a string, it's an immutable object, so we're fine. We don't have to synchronize anything because it never can change. But if what we're doing can change, then we still need more synchronization. So here's an example where we've got a bunch of, we have a field, which is an array of strings with names. And down here, you can see that thread T1 is going to update the QB in the element sub1. We're going to change that to be Manning, or change it to Montana, or whatever, right? Now, QB's is final, which means that we can't change what QB references. However, QB sub1, QB sub 0, QB sub 2, those things can be changed. And therefore, if we're going to change them, we have to make sure that they're properly synchronized by whatever means is appropriate. So it could be a synchronized statement, as we show here. It could be a entrant lock. You could use a spin lock or whatever. But you have to make sure that those things are properly initialized. And that's because changing the contents of a final variable aren't the same thing as changing the final variable itself. You can't change the final variable, but if you can change its contents, then it's not immutable, and then you have to protect it with synchronizers. So I think you'll agree this is some pretty subtle stuff. Again, some of these optimizations are really reserved for people trying to write high-performance objects that run in concurrent systems like concurrent hash map. Most of the time, you don't have to think about that for your own purposes.